Welcome back to our online summit, and you've just arrived at the live lounge, and that means for you, dear guests, you can ask questions or give input, whatever you like. Just use the button on the lower right side, and there you go. So, as we said, today it's about 3D measurement technology, and the opportunities and possibilities are just incredible. Maybe we could just scan the whole building, for example. I can tell you don't see it, it is huge. Or you could scan a body just like me, no problem at all. But you could also scan this pen. And not only that, you could detect every single small crack on the surface. No problem. How and why? Welcome on stage, Michael Kleinkes.
Hello and welcome everybody to the PNF Online Summit. My name is Michael Kleinkes. I'm the Technical Director of VMT, which is a sister company of Pepperl+Fuchs. Today, I'd like to give you an introduction into 3D measurement, into the power of 3D measurement, and I will help you to save money by improving your process. How I will do that? I will be the representative today for 3 companies which belong to PNF. I will come to that later. And I will give you 3 practical examples. Stuff that you can grip, stuff that you can use in your environment and adapt it to your needs. And at the end, I promise, you will have a better understanding about the power of 3D measurement and how to use it for your needs. First, let's make an example. Let's make a journey. Imagine you're walking over a mountain trail. You're on holiday. But it's getting dark, and it's a rocky and steep trail. And you lost one of your eyes, so you're running around there, kind of blind. Everything is black and white. You don't see the rocks. And you try to make your way down to the valley again. You probe the stones. You don't know where you really go. You don't see the signs of the way. That is how vision technology has been up to now, since the last years. Today, imagine you change, it's afternoon, sunny, you see everything and you jump from stone to stone. You see the red and white signs for the way. It's a great day, you enjoy your trail. That is the power of 3D combined with color vision. And that is exactly what I want to give to you in this presentation. Let's go into it and let's do a short introduction, what are point clouds and what is 3D. So we start with very simple stuff. A point cloud. It is a collection of points in space. So we have millions of dots in space with coordinates x, y, and z, which represent a cloud, so a collection of points which are showing an object that you scanned with sensors. You see on the left side in the slide, there are 2 different point clouds, a red one and the blue one. You can just give them one color because there are points in space. They have only 3 coordinates, they don't have any color. They create a grid of your object. What you see here is a car, and you can't even say which car that is because you only see the shape. The display software gives them a color, red or blue, that's it. How do you get a point cloud? You need a sensor. You need something which is creating a picture of your reality. For example, a rotating sensor like this with 2 laser sensors in the middle, rotating around an axis and scanning the environment. This one is a VMT spin-top 3D sensor, and this device is moved by a robot along an object and creating a digital picture of a real scenario. Also, you can use, for example, an R2000 sensor from Pepperl+Fuchs, where the pulse range technology is used to create a distance measurement while a rotating head is moving and the device is scanning a complete circle around itself. So if you take this device and you move it or you rotate it around an axis, you can create a point cloud. Or if you don't want to move the sensor, you can use special stereo sensors which are projecting in the middle of the sensor. This is a VMT light scan model, projecting in the middle via a light frame a pattern and watching these patterns using 2 cameras. This is a one-shot device which is creating a point cloud for you from an arbitrary object. And then you have a point cloud. What do you do with a point cloud? There are several options, and I will dive today into 3 different ways. You can inspect, you can process something, you can automate something, or you can digitize something. You can create a digital twin. And these 3 companies, all belonging to P&F, are doing 3 very different directions and usages of the point clouds. And I will go step by step with you into these examples. We do kind of an experiment. You have the task of solving the problem, and then let's see how we do that with the sensor technology. Now, getting real. I give you an example. How does a point cloud look, and how do we use several sensors to create a point cloud? Let's use a short video which depicts that very good. In this video, you see 3 different sensors combined to one multi-sensor system, and these sensors are scanning a palette with boxes in different shapes and colors, and they create the point cloud out of different direction angles. So using the lasers, moving the devices, you see now color removed, but you have a very nice depicting of the point cloud itself and all the single elements. The sensors are using the reflection of light on the surface of the elements, and they are calibrated into the multi-sensor system by a reference object. And by this, a smart software, which P&F and VMT is programming as frame softwares, can assemble all the points to the point cloud, which is the final result, and which can further be processed to perfectly create a picture of the environment. And when I talk about picture, it is more like a real 3D scenario of the environment. So, that is the example. That is how we do it. Let's get back and see where we go. 3 different views, 3 different companies, 3 different mindset, what to do with the point cloud. And we will dive first into the micro view, the nitty-gritty details. So a task where you have to watch really close. And the second step will be, you don't need everything. You need a special part of the point cloud, the selective view. And in the third step, we go into the macro view. You want everything. You want to see just everything. So in the first step, we focus on the company called 3D Aero. And the task we have at hand is the following. You all are engineers now. You all are confronted by your boss with a new task. Today, you have to solve this problem. We take a combustion chamber. It's a relatively huge object. Let's say it's 3 to 4 meters in size. It's used in airplanes, and this part, 4 meters in diameter, has some micro cracks. You don't know where. You don't know how many. You don't know how bad they are. Your boss says, inspect that part, we want to assemble the airplane again, and we have to fly tomorrow. The problem is, you are a human being. Let's make a sidestep. Humans against technology. There's the task at hand. Humans are very, very smart. Humans are very, very emotional. And that is the problem. We have perfect sensors. We are not aware how good our sensors are. But believe me, as an engineer, if you try to copy a human being, it's crazy, because eyes and brain, fingers, muscles, nerves, that's a perfect system. And we always try to adapt these systems by technology. But on the other side, a human is emotional, a human gets tired, and a human is kind of slow. So we try to create machines which are automatically working, which are perfectly adapted to a problem by special sensors, because they have the advantage. They can remove their eyes and take on another one, better adapted to the problem. And this is exactly what we do here. You as a person, you have the task, control the combustion chamber. It looks like this. And this combustion chamber, because of the size of it and because of the micro cracks that you have to find, was done before with a very ugly process, using chemicals, washing the complete device, the complete element into a very dirty chemical, and then to see the color in the cracks, and then to try to make a very good prediction where the cracks are to repair them. Nowadays, 3D Aero created a huge and very nice project where they completely fully automated this process by exactly doing what we said before, removing the eyes and taking better ones. What you see in the middle is a white light interferometer. That is a very specialized device which is using different light in a bandwidth, projecting this light on the device and measuring the reflection with an accuracy which is far, far lower than a millimeter, going into the thousandths of a millimeter. This device is able to create point clouds which are micro, like a post stamp. And they connected this device, this artificial eye, to a robot, and they moved with the robot automatically around the part, around the combustion engine, and they stitched together every single post stamp 3D point cloud together with the next one, with the next one, with the next one, to have a big, huge point cloud, because it's a good and great and big object, but a resolution which is down to 1/1000th of a millimeter. That's crazy. But let's see how that looks. These are the results. And what you see in the down right edge of the slide, this is the crack. This is a small and tiny crack, which now can be detected in the 3D point cloud due to the very accurate measurements of the white light interferometer. No chance for human beings. No chance for finding all the cracks. And due to the fact that we have an objective 24-hour working system controlled by a robot, the human beings can now control this process, take the data and do other tasks, and not spending the whole day of inspecting the part. And that is your luck. Your boss gave you this task and you said, okay, we can use the sensors and we can solve the problem. Let's call 3D Aero. They have this great setup, and that is the solution for a problem which is using a big device but focusing down on a very narrow part, like the pen that Oliver showed you before. This all is done by 3D Aero. 3D Aero is, like VMT, a sister company of Pepperl+Fuchs. They are located in Hamburg, and they are specialized on research-based projects, mainly in the aviation industry, where they digitize complete airplanes, where they create automated robot-controlled systems to do these kind of special tasks, which need stability, objectivity, and process performance. So far, so good? That was the first step, the micro view, the dive into the 3D point cloud. Now we do something else. We go a step back. We go into the mid layer and say, let's take the point cloud, but only a part of it, the selective view. Why selective? It comes along with processes. Sometimes in a process, you don't need the complete point cloud. You want to focus on an area because you search something, you want to adapt to something, you want to position something. And I like to give you a very practical example also here. And for the one of you who are petrol heads, let's take a motorbike. This is a Harley Davidson windshield, and it's Friday, you have got a new task, your boss comes to you, this is the windshield, find the marked position on the windshield. So somebody else, a perfectly adapted human being who is working since 30 years in the field of surface inspection, marked the point which is not good on this part. Your job is, if this person is marking the bad parts, you have to polish it. And you like to go with a robot to the exact position where you have to polish the defect. The problem here is very special. This is a black part. And you can use a 3D point cloud to digitize the part, and then you get what you see in the middle, these gray result, a point cloud without color. Nice. It's a geometry of the part. What you don't get is the marked point of the specialist. Because this marked point is just a ring done by a pen. This one has no geometrical dimension. You don't see it. It's just gone. Okay, no point cloud. We take a different sensor because we have to see the ring. Other side, right side of the slide. Let's make a photo. We take a grayscale image done by a standard camera 2D picture. We take a photo and you see that it's a kind of dark photo because you want to have a light contrast to the markers. And you can see in the picture the different markers. Easy to detect. That's vision system. Easy to find. But where are these markers on the 3D object? No clue. Now you have a picture, now you find the markers, but still useless. And where do we come here? We run into a dilemma because two different sensors have two different advantages, but also two different disadvantages. And to make it more easy for you to understand, let's dive into a point cloud. An experiment here is, it is a measurement in the office, and we Germans like chocolate, like most of the people in the world, and we took a picture of the desk, and there is a package, two packages exactly, of chocolate in the picture. Let's find it. Here you see the point cloud. We chose a color of blue for the point cloud, and we rotated this point cloud that you can have an impression how that 3D measurement is done, and that it is a point cloud and not just a picture of an artwork. So you see here, where's the chocolate? How could you approach this problem to find the chocolate? It's very difficult because everything is blue, everything is spread in the room. It's a nice and high accurate point cloud, but where's the chocolate? You can zoom in and you can try to find it, but what you see is structure. And sometimes structure doesn't help. Sometimes 3D data is great and you need it, but without an additional information, like your journey in the mountains. You remember when we started your journey in the mountains. It's great to have 3D information, but if you don't see the white and red markers for your way, you're lost. So what we do in the next video is we go to an idea. And the idea is the Pixel+. Pixel+ is shown in the next animation, which is running right now. And this animation is taking a box. That's our object. Very easy, very simple. And this object is digitized by a 3D point cloud sensor. So this one, this collection of points are 3D points. And we take a color picture from the same object. This color picture is moved together with the 3D point cloud data, and there where the picture virtually touches the 3D points, the color of the picture sticks to the 3D point. And that is exactly the idea of Pixel+, a brand of Pepperl+Fuchs, an idea so big that we say, yes, attaching something to a pixel in space, Pixel+. So what is the plus? The plus can be color, the plus can be shade, gray, or even temperature, or maybe in the future smell. Don't know what to do with a smelling point cloud, but. So if we take this picture, if we take this point cloud, and if we bring them together, what you see now, there's the result, a Pixel+ point cloud, which now has color. And what you see in the next animation, we are searching for the chocolate in the picture. We are taking this animation, and it is the same setup. But now we integrate the color information as an overlay using Pixel+ to an area. Now we adapt it, and there it is. The Germans under you, they know it very well. Schokobons and Anuta, that are the candies. And now even for a machine, it is very easy to detect the area. We call it the ROI, the region of interest, in the point cloud to cut off everything else. We don't care about the room. We don't care about the desk. We want to see the chocolate. And we want to process only the data which are in the chocolate area. That is the idea. Taking something additional, a sensor channel like color, like shade, like temperature, and stitch that on the pixels, on the 3D points. And then you can create the advantages of both worlds into your result. Let's move that to a practical scenario. One of the never solved problems is the bin picking. Bin picking means going with a robot into a box, taking a part out of the box, and that is really difficult. Human beings are easy with that. We go into a shop and we are shopping for socks and we search out of the big box exactly the green socks that we want to buy. We go to the cashier, we buy them. Easy. For a machine, that is very difficult because to find the right element in a point cloud, it's just difficult to process. And what we do with Pixel+ is we use exactly what I explained before, a point cloud, a color picture, and then we know exactly there's the object because we know the geometry, and this one is blue. Don't take it, take the red one. Let's see a short video how that works in reality. This video is a demo setup for a fair, which is doing bin picking again with objects which are not really industrial, but people like them. So see that we use exactly again chocolate, but these chocolate elements are representatives for geometries which can change, surfaces which are shiny, and different colors which are normally very easy to see if you have only one color, but very difficult if you want to pick the right color. And you can see here the point cloud on the display, left down corner, and you can see the colored point cloud, and you can see a vacuum gripper, and we go to the red one, and the red one is chosen, not the blue one, and we take this one out of the box, which enhances the process significantly. Before, you just took the parts out of the box. Everything is the same. You emptied the box part by part by part. But maybe one of you has a problem where he says, I have this box, but I need the hot parts, not the cold ones. And if you combine a 3D point cloud with a temperature camera, you can pick hot parts out of the box. Out of parts which are looking the same size, same surface. Some of them are hot, some of them are cold. And that is the basic idea. So let's get back to the real industrial example. We have to solve your task. Your boss came to you and there's still the motorbike waiting for you. So there's a motorbike, there's a Harley windshield. And now you called for VMT, and VMT has a special solution for that where Pixel+ technology is used, where we combine the 2D picture, which you see in black, with vision technology in the software where we mark the different points where the specialists mark the defects. And we take the 3D point cloud of the windshield and we combine both sets. And what you see as a result on the right side of the slide is that is the part in different colors because it's coded in 8, but you can see the cylinders, and that are the defects and their orientation. That is a pose for a robot, so an XYZ coordinate plus orientation, where the robot moves to the part to work on the defect. And that is exactly the solution. We don't want to have the position of the defect. We want to have exactly the vector on the surface where the robot can polish the defect out of it. And that is what we do at VMT. VMT is a turnkey solution provider, 25 years experience in the automotive, medical, and pharma industry, and set up all over the world with different people working on projects to get the process optimized, to guide a robot, and to find the right way to handle parts. That was a selective view. Ready for the last step? Ready for the last task? That is a macro view. Now we get big. We focused, we selected, now we zoom out. The task that you get right now is you are planning a robot industry cell. Look at this. This is business as usual in car manufacturing. Lots of robots, all in different robot cells linked in a street of a production. And there's a model in, and the car manufacturer has this model right now, but the people in the background are planning for the next model, the bigger SUV, the big and fancy one, the one who is driving the company up to top of the market. Question now is, if we have all these robot streets, all that existing production, is the bigger SUV fitting this line? Or do we have to change here everything? And if we don't have to change everything, what do we have to change? And what can we prepare to make the integration process of our new and bigger car model very easy? That is the task. Now it's your turn. Find the problem where the new car is not fitting into the robot cell. And you have two options. Go into the robot cell with a measuring tape and spend the whole week measuring everything. Go there and try to make it happen here, make it happen there, and say, okay, there it doesn't fit because it's too small here. That's a bad task. There's a better option. Espace XD comes there and is using a terrestrial scanner. It's a laser scanning device which is rotating a laser beam and matching a photo with a laser distance measurement. And the idea is the same like Pixel Plus, focused on color. So taking the 3D point cloud, matching the color on it like we saw in the animation, and create a digital twin, a virtual environment. But other than you guys know that from PlayStation or Xbox. It's not artificially designed, but it's a picture of the reality. So you see that on the slide. It's looking like a picture, but you think it's kind of unsharp or dirty. No, no, no. It's a 3D point cloud. We can rotate this element and we can use this measurement. And what can you do now? You can take your robot cell. That is a real one. Dr. Krzysztof has been in that robot cell for hours and days. He knows that cell very well, and he digitized it with every single element which is in there. And here comes a nice story. There's an offline planner which has a CD virtual environment of the cell, and this planner says, okay, I planned this cell, here is the file, somebody else will build it, and at the end it will be like I planned it. His naive view in the office. Then there will be all the guys who construct the robot cell, and they will put a pillar here, they will put a pillar there. Someone said that doesn't fit, we have to saw here, we have to attach and adapt here at the end. The reality is not really the same like the CAD artificial simulation of the cell was. So the problem now is there's something existing, and the way from virtuality into reality, well known and done. But that is not a one-way road. How can we come back? How can we digitize our environment and match it again with our CAD and come back to the guy in the office and say, look at that, buddy. This is how it looks like today after 5 years. And now this guy can take these measurements, this reality, this digital twin of the robot cell, and it is very easy to take the virtual new car body, which is existing in CAD, and move it through the data and see is it fitting or not. And we can use a virtual reality glass and make a walkthrough. We can make measurements, and we can do everything that we want in the office. And you don't have to run around with a measuring tape. And that is exactly what Espace 6D is doing. They digitize environments. They measure robots. They integrate robots into CAD files and see that everything is fitting and that your industrial environment is what you want to have, and that you guys in the office know exactly what is up on site. And now, coming to the end. That's the great wrap-up of everything. That is the idea that I like you to take home. I like to give you a better understanding what to do with point clouds and where the power of the 3D measurement lies. And these are the 3 out of several different views on point clouds. The micro one, diving into it, finding everything. The selective one, taking a region of interest. And the huge one, the macro one, digitize the building. And all that can be done by companies belonging to the green Pepperl+Fuchs family. We are all sister companies there, and we have our mother, Pepperl+Fuchs, and we will discuss that in the next sessions, and I want to thank you. I want to thank you for your attention. I'm hoping that you get something out of that, that you are able to adapt these new insights that you hopefully got to your problems, and I wish you a wonderful day, and hope to see you later in the chat and to answer your questions. Thanks a lot.
Thanks, Michael. Wow, that was mind-blowing, and I can see many open mouths out there from here. I'll take a deep breath. That are really, this is almost impossible to imagine what is possible already. And you said one thing, I have to look at my paper. So you can scan arbitrary objects and you can create point clouds. Okay, got that, but is it possible to have, arbitrary big point clouds?
Yeah, that is the funny part and the interesting part of it. Let's take a sensor. And we have one sensor, we make a measurement. And for example, the R2000 has a measurement range which is defined, right? And we want to scan the complete building. So we come to a situation where one sensor is not enough. You have 2 options. You can move the sensor to different locations and calibrate everything, or you can take 10 different sensors and bring them together. So there are no limits of the size of an object that you want to measure, because you can modularize the system. You can use multiple sensors to combine them to one system, or different positions to combine the measurements. So no limits to the upper part, no limits to the down part, no limitations at all.
No limitations at all. We talk about that later, what possibilities that opens. But how long does it take to process all these data?
Yeah, that is a question our customers always ask. How long does it take? We need it now. We need it in 0 seconds. Yeah, we need it fast. It is a complete different technology, like taking pictures or making one distance measurement for sure, because most of the point clouds have millions of points. What we do is we take these point clouds and we process them with specialized hardware. We can use standard industrial PCs, or we can use special number crunching units on graphical cards in the PC to enhance that process. Nevertheless, how big, how good your hardware is, you can't process in milliseconds these millions of points and attaching color to it and extracting the region of interest, match the part and create the result and documentate everything. It takes seconds, but it's depending on the size. So if we have a small area, it's kind of half of a second. If you scan this building, you will need several seconds to do it.
If you scan my body, for example, and you want to look for maybe that one gray hair.
Oh yeah, several. If we scan your body, so you are 1.80 meters and your volume is it will take a few seconds. Yeah. So we will scan your body with a velocity or whatever, but it will take 2 or 3 seconds to create a point cloud and to process it another 2 or 3 seconds.
Okay, but for me this still is pretty fast.
Yeah. Yeah, for sure. And we make it faster every day. Yeah. So in a few years, that will be enhanced by the technology that we have right now, and by the integrated calculation that sensors will be and will have in the future more and more.
And we'll talk about that later in our networking lounge with Thomas Damaschke and Adrian Kryschak, you already mentioned, and then maybe about enhancing technologies like AI and so on. So thanks again, Michael Kleinkes. That was a wonderful presentation. And once again, if you have any questions, just ask. And for the networking lounge, which starts, give me a second, in exactly 24 minutes, you have to change the room. So just click on to conference and we'll be back in our networking lounge. See you there.